Start us off. Oh,
all right. All right. Well, good morning, everyone. I think I can hear the bird chirping in someone's Zoom, probably Tim's. That means it's early in the day. So welcome. And it is my great pleasure to have you all here for Iwnetim Abate's thesis defense, also known as Tim. And together with Tom Devereaux, we have been advising Tim's PhD thesis over the past 5 years. So let me just say a couple words on the scholarship and some personal remarks. This line of research was started in the True Group about 7 years ago. And we already had, prior to Tim's work, 2 other PhD theses on the topic. And to be frank, I thought I would no longer be surprised by this topical area. But thanks to Tim's tireless effort, I was proven wrong. Despite the significant progress that was made, Tim really took it to the next level. And I will not talk about the details. I'll let Tim introduce the topic. But what was necessary in order to achieve this level of new understanding of the phenomena that Tim will present today are 2 reasons. One, Tim had a real eye for combining chemistry and physics, which is essential here. And then secondly, he was also passionate about pursuing both experimental work and theoretical work at the same time. And by combining these traits, he was really able to push the field along and discovering things that we couldn't even imagine just a couple of years ago. So I'm sure Tim will show you all that he has learned momentarily. On a more personal note, as I think about what are the qualities that Tim possessed that really impressed me the most, it really comes down to two qualities. Number one, I think Tim, above all, is a persevering scientist. Many people have witnessed his tremendous growth over the past couple of years, but fewer people know all the challenges that comes along with it, and battling the reviewers and getting papers published. And never one time do I feel Tim has lost his drive to get things done. And I think it's with this very conviction that he was able to arrive at his outstanding endpoint of his PhD today. And then secondly, I think Tim is a very strategic thinker. So in addition to the excellent scholarship, he also thinks carefully about what to do next and plan things out. And I think that really further enhances his productivity, which again, you'll see just in a moment. So Tim, very proud of your achievements. And let me now hand it off to Tom, who will say a few more words.
yeah, thanks. Thanks, Will. Tim, and for everybody else, it's always a bittersweet moment reaching this stage. It's great to acknowledge a transition in the trajectory of students, and with Tim, it's particularly exciting and bittersweet for me, because you see, Tim to me is an ambassador. He served as a incredible liaison that brought, a lot of times, the different language that we speak in certain areas, in physics and material science and experiment and in theory, together. And he's been able to guide me through a tremendous complex landscape that is battery electrochemistry, as well as the application of synchrotron techniques to be brought to bear on these problems. And I've learned a tremendous amount from him. And as part of the process, even just deciphering a common language to speak is often 90% of the effort required. And and through it all, I don't want to go on and on, but I'm sure people know also that Tim is an ambassador when it comes to actually working with people from different countries and bringing activities back to his home country in Ethiopia as well. And he does it all with a remarkable optimism and remarkable great sense of attitude that is just been a joy and delight to work with. So that's all I want to say at the beginning, and let me just turn it over to Tim.
Wow. Thanks so much, Will and Tom, for your excellent remarks and very encouraging words. I really appreciate it. And I'll take a time a little after my talk to also reflect about what I've learned from you two. But thanks so much again for introduction. And thank you all for coming today. Wherever you are, good morning, good afternoon, good evening. It's a huge pleasure and privilege for me to share with you my work that I have been working on the past couple of years. And as Will and Tam indicated, what I have been working on is on issue of energy storage, energy materials. So, I'm gonna share with you what I have been working on the past few years on this topic. So, give me a second. Yeah, so as you know, global warming, portable devices, and electrification has been the major drive for electrochemical energy storage. But the issue that is closer to my heart is the issue of energy accessibility. I suppose Will and Tom mentioned, I grew up in Ethiopia, an eastern part of Africa. And here is the map of the world at the evening, where you can see Africa appears to be dark compared to the rest of the world. And only 4 out of 10 sub-Saharans have access to the grid. So growing up in Ethiopia, a typical night involves, for me, using a kerosene or a candle to be able to do my homework at night. And because of this limited energy accessibility, we have to resort to using wood or charcoal to be able to meet our energy demand. And this has adverse effect both on our health and also on the environment. And this is despite the fact that there's an abundant renewable energy sources, including solar energy in Africa. However, as you know, renewable energies are intermittent, which means the peak supply from those energy sources doesn't match the peak demand. Therefore, we need to be able to develop devices that can store these renewable energies for a later use when there is a demand. One form of such device is what's called batteries. And batteries are made up of 3 components. The first one is what we call the negative electrode, or the anode. And the commonly used lithium-ion batteries, which we use in our phones, in our laptops, and now in our cars, the anode is mainly elated graphite. The other part of the battery is what's called the positive electrode, or the cathode. And these are mainly transition metal oxides, such as lithium cobalt oxide. And 2 years ago, the Nobel Prize for Chemistry was awarded for the discovery of such material. And this is what enabled the lithium-ion batteries as we know them and portable devices as we know them today because of such discoveries of lithium cobalt oxide about in the 1970s. And between these 2 electrode materials, there is a medium that conducts ions during charging and discharging. And this medium is what's called electrolyte, and they are mainly made from a solvent and a salt. So what happens when we use our batteries is that the lithium ion and the electron move from the anode to the cathode. However, the electrolyte is only permeable to lithium ions, which means the electron has to go to the external circuit, thereby powering our device, whether it's a battery or a car or a laptop. And then when we charge our battery, what happens is the exact opposite, where the lithium electrons are moving back from the cathode to the anode. So I would like to mention over here that if you look at these 2 materials closely, they are what we call layered materials, which is we have a layer of material and there's a gap between them, which we call a van der Waals gap between the materials which we store the ions. Because of such characteristics of the material, the way we store lithium ions in this material is called intercalation or ion insertion, because we are inserting ion between the gaps of this material. So, however, current batteries have several limitations in order to achieve our global energy needs. For example, we have this ambitious goal of having a 90% renewable energy penetration by 2050. And also currently, about 45% of the world lack reliable power. And current batteries are limited to achieve such demands because of 2 main reasons. The first one is they have a limited energy storage capability. That means the amount of energy they store is very limited to address these issues. And 2, they are very expensive. For example, if you take one Tesla car, about 1/3 of the cost of the car is coming from a battery. So my work has been focusing on, with others in my group, to be able to find materials where we can actually address these two main challenges. Namely, I have been focusing on trying to replace this material, which I call lithium cobalt oxide, with other materials that has more energy density, but comes at a low cost. And I broadly explored this for both lithium ion and sodium ion battery applications. So before I take the time to share with you what I have learned and discovered in the past couple of years, I would like to mention some key terms that I'm going to commonly use throughout my talk. The first one is what we call the voltage capacity curve. This is a curve that we use to characterize the property of the materials. And here is the voltage in the y-axis and the capacity in the x-axis. Here, capacity refers to the amount of charge or the amount of electron you can store or remove during cycling. And what happens when you move from left to right on this curve is dilithiation, removing these lithium ions from the material. What happens when you move from right to left is lithiation, putting back the lithium back to the material. And the amount of energy you can store in a given material is given by this formula, which is the voltage times the capacity. In other words, the area under the curve, and I'll come back to this formula later on. But also the two main characteristics that I would like to draw your attention to is if the gap between the forward and the reverse process are very small, shown over here, we call the material to have a small hysteresis. If the gap in terms of the capacity is very small, we call it the material is reversible. However, there are several materials where both the hysteresis and the capacity or the reversibility are very poor. So in my title, I mentioned that the goal is to design materials with hysteresis-free high-valent redox for electrochemical application. And this is such a quite mouthful title, but my goal today is to try to educate you about what it means by each component of this title. So first, I will start by defining what I mean by high-valent redox and why that's relevant in terms of finding next-generation materials that can replace the current technologies and improve capacity and draw costs down. Second, I will talk about the challenges we commonly observe when we try to apply this high-valent redox in order to improve the performance of battery materials. Last but not least, I'm going to talk about how can we actually avoid those challenges to actually harness the positives of high-valent redox without its consequences, without its challenges. It's going to be the key question that I'll address during my end of my talk. So first, I will start by defining what high-valent redox means. So in order to define high-valent redox means, I would like to draw a parallel with what we call as low-valent redox. So what we call low-valent redox is a redox process that nominally involves a low valence state of a given element. For example, iron plus 2 to iron plus 3, which is the low valence state of iron, we call this process a low valent redox. However, in high valent redox, we nominally involve higher valence state. For example, iron plus 3 to 4 oxidation, as opposed to 2 to 3 oxidation, it's called the high valent redox process because we have high valence state of a given material. And as you can see, the energy required for this process is higher than for the low valent redox. Because of such difference in energy, when you put this energy to involve high-valent redox, the material tries to respond to become stable by forming a short covalent bond. In other words, there is a stronger driving force to form a short covalent bond in high-valent redox systems as opposed to low-valent redox systems. And then last but not least is this high-valent redox process takes place at high voltage. Since energy we can store in a given material is capacity times voltage, and since high-valent redox offers us high voltage, that means we can improve the energy of a given material by improving the voltage through high-valent redox. And this is why high-valent redox is relevant for improving the energy density of the battery materials, because it happens at higher voltage. Like I mentioned, one of the definitions of high-valent redox is there's a stronger drive to form a short covalent bond. Based on this definition, we can actually classify high-valent redox into two different mechanisms. The first one is if this short covalent bond is formed between a metal, like a transition metal and oxygen, shown over here, we call it a cationic redox because the metal is a cation. If this short covalent bond is formed between anions, in this case, oxygen anions, in the form of peroxide, oxygen gas, we call this ionic redox. And such classification of the high-valent will allow us to understand the exact mechanism of high-valent in the material, thereby using the understanding to be able to engineer materials with higher capacity and lower cost. And to be able to classify these mechanisms, we can use different spectroscopy techniques, and I will talk about them in the coming slides. So first, trying to look at one of this next generation material, which we call the lithium-rich NMC. NMC stands for nickel, manganese, and cobalt. And here we are replacing some of the cobalt with manganese and nickel to drive the cost down while improving the energy capacity. And this is one of the next generation material with hope of replacing currently existing technologies. If you look at the voltage capacity curve of this material, there are two steps. The first one is a cationic redox, and the second one is this ionic redox. And this black curve for lithium-rich NMC is very different from the dotted red curve, which I'm showing for lithium cobalt oxide, which we currently use in our batteries. And if you compare the red one and the black one, there are two major differences. The first one is, in the black one, since we have ionic redox, the amount of charge or capacity we can store is higher than the lithium cobalt oxide. Therefore, this ionic redox is allowing us to store more capacity compared to lithium cobalt oxide, which we use currently. The second difference is that the gap between the forward and the reverse process, which we call hysteresis, is larger for lithium-rich NMC, shown in black, as opposed to lithium cobalt oxide. Therefore, this ionic redox mechanism is allowing us to improve the capacity as shown on this curve, but it comes with a cost, and that cost is there is large hysteresis and there's a huge gap between the forward and the reverse process. What this gap means is we are having a source of energy loss. So like I mentioned, energy we can store in a given material is given by capacity times voltage. In other words, the area under the curve is the energy we can store, for example. And here shown in green is the energy we can store. Shown in blue is the energy you can remove. But because of this large hysteresis, we have a dead energy shown in the red curve. Therefore, large hysteresis means we have more energy loss, and that's not favorable. So ionic redox, even though it can improve capacity by almost twice, it also causes large hysteresis or energy loss that has to be addressed. So this concept of ionic redox is not limited to batteries. For several years, scientists have explored this idea for application, including catalysis or fuel cell application. For example, in the field of catalysis, people have investigated the impact of oxygen band in a given material to the activity of the catalysis. For example, here is showing a different catalysis material for a given reaction, and their activity is highly dependent on the ease of the oxygen to involve in such reaction, or what they call ionic redox. In addition, in the field of fuel cell, people have also explored the exchange kinetics of a given material for fuel cells, highly dependent on the involvement of the oxygen for such process. Therefore, ionic redox can improve capacity in batteries, can improve activity in catalysis in fuel cell application. Therefore, understanding the science behind it will help us to design reaction in devices with better performance for energy storage and energy catalysis. So the question is therefore how can we understand the cause of the hysteresis in this mechanism while we harness its benefit for capacity and activity. So this brings me to the second part of my talk, which is trying to understand this challenge. The challenge here again is the hysteresis that causes energy loss whenever we have ionic redox. And we want to understand what is the mechanism and what is the source of this hysteresis in order to be able to avoid this challenge. So we use several techniques to be able to answer and understand these challenges. The one technique that I'm going to heavily use throughout my talk today is called RIX. RIX stand for resonant, inelastic, X-ray scattering. It's a method we use to characterize the electronic structure of the material. There's a two-step process when you perform this measurement. The first step is we come in with certain photon energy to be able to excite electron from the core orbital, in this case, oxygen 1s, because we would like to understand the oxygen. And this excitation process will move the electron from the core to unoccupied orbitals. This is the first step, and that leaves an intermediate state that is not stable. Therefore, in the second step, this electron that's excited and other electrons in the occupied orbitals will jump in to fill in the core hole. To conserve energy, this jumping process will emit a photon that can be collected using a detector. Since RIX involves two steps, the information we get from this measurement is a three-dimensional data that's plotted in such manner, where I'm showing the incoming energy from the first step on the y-axis and the outgoing energy from the second step on the x-axis. And what's shown as a bright feature over here are the photons that are collected from the second step. If you actually integrate these bright features or the bright photons onto the y-axis, you'll be able to obtain information that's similar with what we call X-ray absorption spectroscopy, and this might be more familiar to people who use spectroscopy. They are not the same, but they are very similar information contained to the different techniques. So we perform this RIX measurement at the Advanced Light Source at Berkeley, and we complement this experiment result with computation using a first principle code for colloidal spectroscopy called Ocean. And you can learn more about the accuracy of this method to study oxide system in our recent paper shown over here. So using this RIX techniques to understand the property of this lithium-ion MSC material that I introduced a couple of slides ago. So in the pristine state, we have a RIX map that looks like this, where we have a bright feature that's coming around 525 eV energy in emission energy. And this bright feature is actually coming from excitations or emission process from the metal oxygen hybridization process over here. But what I would like to draw your attention to is what happens after charging. So after charging and after anionic redox, here is what the RIX map looks like. And as you can see, in addition to the bright feature that exists in the pristine state coming from the metal oxygen hybridization, we have this peculiar feature that's appearing around 531 eV in incoming energy and 523 eV in emission energy. This peculiar energy tells us that upon anionic redox, we are forming a new species in the material that can describe the mechanism of anionic redox. Since we commonly use this feature whenever we have anionic redox, in the field, we have been correlating this feature with anionic redox. So the hypothesis is, since anionic redox causes hysteresis or correlated with hysteresis, and since this feature also correlated with anionic redox, can this feature tells us the mechanism of anionic redox, also why we have hysteresis? So based on this hypothesis, I would like to classify this into three main questions. The first one is, what is the nature of this oxidized species that we are forming on the RIX map? Second one is, once you know what this species is, what is the mechanism that's causing the hysteresis? And third, but not least, is how can we decouple this correlation between this feature and hysteresis to be able to engineer materials without hysteresis, without the energy loss, while harnessing the benefit of high-valent redox. So, we can view this problem, these questions in a different way. We can think of the first two questions regarding the nature of the species, also the mechanism that causes the hysteresis, as a way to identify the challenges behind hysteresis and behind high-valent redox. You can see the third the third question is towards designing material that can harness the benefit of high-valent redox without its cost, in this case, the energy loss or the hysteresis. So first, I'll make an attempt to answer the first two questions. So there have been several scientists throughout the world who have been proposing different mechanisms to understand the nature of this anionic redox in such materials. The first hypothesis or argument is that whenever we remove, lithium ions, whenever we charge the material, what's happening on the oxygen is we are forming localized holes. There's another argument that says that instead of forming a localized hole, what happens with the oxygen is the oxygen atoms come together, they form an oxygen gas. That oxygen gas leave the system as you do ionic redox, therefore leaving behind a system that is less stable. There's a similar but different argument here, where instead of the oxygen atoms leaving the system, they are actually staying in the material by forming a short covalent bond close to 2.4 angstrom and forming this oxygen dimer as shown over here. And another argument that has been proposed recently by our group about 2 years ago is instead of forming oxygen bond with 2.4 angstrom, we are indeed forming oxygen bond with a bond length close to 1.45 angstrom. And in addition to that, we are forming a metal oxygen double bond. So as you can see, there have been different proposals to understand the ionic mechanism. But my hope today is trying to narrow down and see which one is the most accurate to describe what's going on in the materials we are studying. And to be able to answer this question, first we have to understand the chemistry behind whenever we have ionic redox. So in the pristine material, we have the material in oxide state, that is O2 minus. When we do ionic redox, when we charge, what happens is we remove electron from the material. Therefore, we have O minus, or as a physicist likes to call it, holes on oxygen. But however, the O minus is not stable. Therefore, the O minus would like to form a dimer oxygen-oxygen bond as a form of peroxide, superoxide, or oxygen. So this is the fundamental chemistry of what happens when we perform ionic redox in these oxide systems. Based on this understanding, I performed Rick's simulation, trying to understand what is the source of this feature we are observing in the cathode materials. So, these are the different oxide systems that I mentioned in the previous slide that can be possible scenarios whenever we have ionic redox. And we performed ocean calculation using Rick's calculation using ocean simulation code. And here is the Rick's map of the different oxide species. And as you can see, all of them have a different localized feature at a different energy scale. But the one that has a feature very similar to what we observe in the battery material is what's coming from a peroxide. So the peroxide is giving a feature very similar to what we observe in the cathode material. And if you look closely, this feature is coming from intra-band excitation from the sigma star to the pi band of this peroxide system. We also performed an Rick's measurement on reference compounds containing either a peroxide or a superoxide. And here you can see that the peroxide containing reference compounds have a similar feature, very comparable to what we see in the battery materials. However, both these compounds we use for reference compounds for measurement or for simulation, they don't have a transition metal, which is the biggest component of the cathode material we use. Because of this lack of transition metals, they lack the complexity of metal oxygen hybridization. Therefore, these results are preliminary but not conclusive. So what we decided to do moving forward is that how can we further resolve the different oxide species using either their bond lengths or their bond vibration. So the previous slide was based on the electronic structure, but here you can see that the different oxide species also have a different bond lengths, have a different bond vibration. So one can use Raman spectroscopy to measure this bond vibration. And a typical Raman spectroscopy for cathode material is shown over here, where I'm showing the Raman spectra of the pristine material shown in black. As you can see, there's the EG and the A1G bonds are coming from a vibration in the different planes of the material. The D and the G are coming from the small amount of carbon we add to improve conductivity. But the most important change I would like to draw your attention to is what happens when you charge. So when you charge, as shown in this red curve, we have this new peak forming around 800 wave number. And this 800 wave number is correlated, has been correlated with a peroxide presence in a given material. We also use a technique called neutron pair distribution function, in short neutron PDF, as a method we use to measure the scattering lengths or the bond lengths between two neighboring atoms. using Neutron PDF to look at battery materials, we found out that the metal-oxygen bond is close to 2 angstroms, and the oxygen-oxygen separation distance in the pristine material is close to the 3 angstroms. But the most important change, again, what happened upon charging is, in addition to the pre-existing peaks, we have a new peak close to the 1.5 angstrom from the Neutron PDF measurement after ionic redox. And this bond length is very close to the peroxide bond length. And this wave number that I measured from the Raman spectroscopy is also very similar to the peroxide species. So what we like to argue here is that when we have ionic redox, we form oxygen-oxygen dimer with a short bond length. And from using the Raman and the Neutron PDF and the Rick simulation, it indicates that what we are forming is a peroxide dimer with a bond close to 1.5 angstrom bond length. But the most important here is actually the fact that we are forming a short covalent bond between 2 oxygen atoms. In this case, happens to be the peroxide. So now we answer the first question. That is the nature of the species we are observing on the Rick's map upon ionic redox is a peroxide-like or a peroxide species with oxygen-oxygen bond length close to 1.5 angstrom. Now we know the species that has been correlated with ionic redox and the hysteresis. The question is, why does this short covalent bonding between oxygen atoms is causing the hysteresis that we commonly observe when you have ionic redox? So to understand this mechanism, I'll again go back to the first thing that I was saying about the chemistry behind ionic redox. So what happens when you have ionic redox is that we are removing electron from an oxide O2- state in the pristine to O- state. However, the O- state is not stable thermodynamically. Therefore, we end up forming oxygen-oxygen bond lengths close to 1.5 angstrom. It happens to be the peroxide dimer. And this stability from point of thermodynamics is what's also leading to forming this short covalent bond that's causing a local bond strain. What I mean by that is, in the pristine material, as measured from the Neutron PDF, the oxygen-oxygen separation distance is close to 3 angstroms. However, upon ionic redox, we are forming oxygen-oxygen bond that's close to 1.5 angstrom bond length. And this is a significant change in the bond length that's inducing a local distortion and a local bond strain in the material. And the material tries to alleviate this strain by moving the transition metal to a different site, what we call as a cationic disorder or a transition metal migration or hopping. So what I mean by this process is that if we have such layered system that I mentioned in the beginning of my talk, that these are layered systems where we have a lithium in the between, and then we have the metal on the transition metal layer. Upon charging is we remove the lithium, leaving back this backhand site in the system where actually the transition metal can move to occupy this site, thereby alleviating the bond strain created by this short oxygen-oxygen bond formation. We actually confirmed this, understanding using experiment, using X-ray diffraction. And here's again the discharge profile of lithium-rich NMC, as shown over here, where the cationic and ionic redox steps are shown over here. And as you can see, what I'm showing in the bottom curve is the amount of migration as a function of capacity. Here you can see that this amount doesn't change during cationic redox. However, we have a linear change in this quantity as we have ionic redox. Thereby, this could explain why we could have this cation disorder to alleviate a short bond strain that's created by the Proximal formation. So we can actually summarize this understanding in a very simple schematic, as shown over here. So what happened in the pristine state is that we have a layered system in the form of an oxide O2- state. Upon anionic redox and upon charging, we form a short covalent bond with a bond length close to 1.4 angstrom. And this is accompanied by a cationic disorder to alleviate the bond strain. Therefore, this leaves us a very disordered material. Therefore, the path one would follow from moving left to right is very different from the path one would follow moving from right to left, because we have a different structure points for two pathways. Because of this path dependency, we have what's called the voltage hysteresis that has been shown in the past few slides. So this explains why we have hysteresis and why we have path dependency. This is because of the cationic disorder and the peroxide forming this configuration that will affect the pathway moving from left to right and right to left. So this answers the second question, that the mechanism behind the hysteresis is that the peroxide formation coupled with catalytic disorder is causing material instability that causes hysteresis. So this is very disappointing and discouraging, because with hopes of improving capacity in these materials using high-valent redox, now we are facing this unavoidable thermodynamic penalty, which is causing a peroxide formation and causing a disorder. But the question we like to ask is, can we actually circumvent this pathway to be able to design materials we can still achieve or harness the capacity without the hysteresis, without the disorder? So this brings me to the third question, is how can we prevent the formation of this peroxide formation in this material and their accompanying catalytic disorder? And like I mentioned in the previous slides, so far, I have shown that when you charge and you have ionic redox, you go from an oxide state to the O-. The O- is not stable, therefore we have a covalent bonding. The covalent bonding from a very short covalent bond, short bond length that causes local distortion that has to be limited by migration, and therefore this causes hysteresis. And this is the pathway that has been limiting us from achieving the capacity of high-valent redox. But the question I would like to ask is, can we actually prevent this pathway? Thereby, we can prevent the formation of covalent bonding while we stabilize the O- species as they are, and without having this local distortion and catalytic disorder. One can think of doing this or addressing this problem in two different ways. The first one is one can think of finding a way to design a material where we have a material that has a large kinetic barrier for the O- species to form a peroxide. Therefore, in a typical cycling condition, we won't be observe this peroxide formation and the O- are stable as they are because of the kinetic barrier. Another is approach from thermodynamics, where one can think of a material design principle where we actually reverse the stability of this oxide species. Therefore, as opposed to the peroxide being more stable, can we make the O- to be more stable through material discovery and material synthesis? So it turns out that there is a material that behaves in a way that we can actually prevent the peroxide formation and stabilize the O- species. And I will tell you which of the two mechanisms is the one that is helping us to understand the mechanism behind such material. And this material is what we call the sodium manganese oxide, as shown over here. As you can see, 1 out of the 7 manganese atoms are missing. So if you look at from the top down of this material, you can see that there is 1 out of the 7 manganese atoms are missing in ordered fashion. And I'll come back to this ordered fashion point later on, as it's very relevant to explain the behavior of this material. And this material can also be written simply in such formula, and I will use this formula from now on to describe and to refer to this material. So if you perform ionic redox on this material, this is what it looks like. You have an exceptionally low hysteresis during charging and discharging. And this low hysteresis is measured to be close to 40 millivolt, and that is maintained for several cycles as shown over here. If you actually compare this small hysteresis with previously reported lithium-based and sodium-based cathode materials, here is showing the log scale of the voltage hysteresis. Our material had a very small hysteresis compared to previously reported sodium or lithium-based cathode materials that had ionic redox. So the question is, how we indeed achieve this exceptionally low hysteresis in such material? And did we indeed actually prevent the peroxide formation in stabilized O- species in the material to be able to achieve this exceptionally low hysteresis? To answer this question, I again turn back to the method that I introduced at the beginning of my talk, which we call the RIX. And here is the RIX map of this material in the pristine state. As you can see, we have this bright feature we commonly observe because of the manganese atom oxygen hybridization. But the most important change again happens after charging, after ionic redox, where we see, in addition to the bright feature we commonly observe, we also have this faint feature that appears close to 527 eV. If you actually plot this information a different way by integrating this bright feature onto the y-axis, this is a similar information plotted in a different way, where I'm showing the pristine material in the black line and the charged material in the blue line. As you can see, the most important change happens around 527 eV by formation of this new peak upon charging. And this is obviously very different from what you observe in the NMC material, where we have the hysteresis, where you have this feature that's coming close to 531 eV, but this one's 527 eV, indicating that we're not forming a peroxide in the sodium manganese system. We are forming a new species over here, which might indicate that we are forming the O- species. To confirm this, I turn to density calculation with my colleagues, where here is the unit cell of the material shown the manganese and the oxygen in the sodium atoms in magenta, red, and cyan color respectively. And upon charging, the most important change after removing the sodium atoms or upon charging is that we are forming these dampier-looking structures, which predicted to be the O- species from the density calculation. And like I mentioned, this system has a very ordered defect. And this is very relevant because the oxygen atoms near the vacant site, shown in blue, have a different local environment, different electronic structure compared to the oxygen atoms away from the vacant site. And such difference plays a role in terms of stabilizing this localized hole or O- species. If you actually, based on this understanding, if you perform a simulation of the XAX of this material, you see that this pre-H feature we are observing in the charged system shown in the experiment is actually coming from two oxygen atoms where we have the O- species. So in other words, the O- species are giving us this pre-H feature that we uniquely observe in this material that's correlated also with the low hysteresis. So we indeed form O- species in the material, and this might explain why we also have the low hysteresis in the system. So the question then is like, why this O- species are only stable in the system when having been discovered previously by a different system that has been explored for the past 10, 12 years. To answer this mechanism of stabilization, we explored different O- configuration or hole configuration in the system, are shown over here, but we found out that the most stable configuration is what we call the split hole problem configuration, are shown over here. And this whole configuration we found it to be as a configuration that maximizes the charge screening, maximize the Coulombic stabilization between the holes that are formed and the sodium vacant sites that are left behind. Such Coulombic interaction is highly enhanced in such configuration, and that's why this system is the most stable one, and that's why the holes are stable. We also compared the stability of the O- species with a peroxide and with a cathodic disorder, as shown over here. So even though what we observe experimentally is the O- species, we found out that the peroxide system with the cathodic disorder is actually more stable thermodynamically, but we don't observe it experimentally. And this explains that there's a kinetic barrier that actually prevents the O- species to form the peroxide formation with cathodic disorder. So in fact, we confirmed this density calculation using an experiment where we see this pre-H feature that we now confirm it to be the O- species is stable, is reversible for several cycles. However, if you perform the Rix measurement after a couple of days, giving it enough time for the O- to overcome this barrier, you would actually have the O- species to disappear, and instead you form a new feature over here that indicate that we are forming oxygen bond formation or dimerization. So this indeed confirms that there's a kinetic barrier that is limiting the system from forming a peroxide and helping us to stabilize this O- species, which is helping us to have the low hysteresis. And the question is why this is unique to this material. Is in this material, like I mentioned, there's an order defect. Because of order defect, the number of hopping sites required for migration of a cathodic disorder is higher than previously reported systems. And therefore, one can think of this, this design principle where we introduce defect in a given material in order fashion to be able to improve Coulombic stabilization, thereby stabilizing the O- species through the Coulombic interaction, but also improving the kinetic barrier to form a peroxide or a dimer formation. So this will be the design principle that we like to take away and apply to other lithium and sodium systems to achieve such exceptionally low hysteresis we observe in this material. So we indeed are able to circumvent this reaction pathway. We indeed are able to prevent proximal formation and stable domain specieces. And the way we're able to do that is by improving chemical stabilization and kinetic barrier through order defect introduction in the system. So the key findings in this work are threefold. The first one is this is the first report of hysteresis-free anionic redox system, where we unambiguously confirmed that this O- species formation is the mechanism behind this hysteresis-free system. This is also the first report where O- species are stable at room temperature. So this could be very relevant not only for battery or for application including catalysis, where people want to use O- based systems to actually improve catalytic activity. And also in the field of solid-state chemistry, whenever we discuss anionic redox or high-valent redox, we mainly focus on the idea of covalent bonding as formed and a combining local distortion. But here we introduce a third, also a very important triad, what we call the Coulombic stabilization. And third but not least is the O- species, or the whole configuration we discover is the first of its kind from our understanding. And we term this whole configuration to be the split hole polaron configuration. What I mean by the split hole polaron is that as opposed to the hole being localized on one oxygen, it's actually shared with the neighboring oxygen, therefore it's split into two. And this is a very exotic species that one can actually study this for quantum property, its quantum property, and one can also use interpolation as a way to actually discover new exotic species that can be relevant for the field of quantum matter physics and for the field of quantum material studies. So at this time, I answered also the third question, which yes, we can prevent the formation of the peroxide and such a disorder. And the mechanism is by stable domain species and the disorder through the order defects. So, like I mentioned at the beginning of my talk, current batteries have several limitations, mainly on the area of having energy capability to address our energy demands, but also in terms of the cost, like I discussed in the previous few slides. But hopefully, by the end of my talk today, I was able to convince you that high-valent redox, and namely anionic redox, is actually another very promising pathway in order to improve the capacity of such materials at a low cost. And whenever we try to do this high-valent redox introduction or anionic redox in this material, we have been observing challenges due to the thermodynamics and the covalent bond formation, the drive to form that. And my work showed that we identify this mechanism, why we have short covalent bonding, but we also identify a way to actually prevent these challenges to be able to harness the anionic redox without its challenge, namely the hysteresis. So now we have an exceptionally low hysteresis material with improved capacity from anionic redox for the first time. So with that, I will thank you for your attention, and I'll be happy to answer any question you might have. And you can also, after this, reach out to me via email or Twitter to ask me any questions. And you can also go through our papers to learn more in detail about what I was able to present today as portion of what we have been able to do with my colleagues at Stanford. So thank you again for your attention, and I'm very happy to answer any questions that you might have.
All right. Thank you very much, team. We're now open for questions.
I think Michael raised his hand.
Hey, Tim, excellent talk. I have a question. I'm convinced about the stability of the oxygen hull. You did a very nice job of that versus the peroxide formation. And then you were mentioning these things because I come from a catalysis background. You were mentioning, about designing catalysts, about using the anionic redox potential for the batteries. So my question is, are these potentially in practical application, mutually exclusive in the sense that if you're stabilizing these holes, and I'm thinking, on the surface, would you make the material more catalytically active, say like formation of an SEI layer in that sense, versus, you know, the internal dynamics of, you know, increasing capacity? So I'm just wondering if you can comment on that a little bit.
Thank you, Michael. So if I understand your question clearly, so the question is trying to use all species for relevant application without the consequence of like side reaction on the surface, like ACI formation, for example. That for the most part.
Right. So if you increase capacity, do you increase catalytic activity as well?
Yes,
potentially.
Very good question. So one thing to understand about this species are they are bulk species. You know, for example, from a limited understanding of the catalytic field, people use, like, for example, titanium oxide, and they have reported maybe formation on the surface. But here is like a bulk formation of the species. So now the question is, like, you know, what happens in a real application for catalytic application when you have surface reactions and the stability of that. So I guess, so one thing we were able to do on this work is that it really depends on the voltage window you are playing with and the stability of the environment around it. So the goal over here was trying to understand and discover this species without, you know, avoiding all these noises like ACI formation or side reactions. And we did a very careful job where we actually try to create a very clean surface, but also try to narrow the voltage window. Thereby we will avoid any side reactions, ACI formation, in a way that affect the results. Because what we were hoping for is to see this species in a clearer fashion possible. So that's been, you know, the work that I have done so far. I think, for example, if you're actually able to design electrolyte systems, for example, where they are still at high voltage, I don't see, you know, an issue where this could be still relevant in terms of catalytic application, where they actually won't be suppressed by surface reactions. But the work we have done so far is like trying to avoid those, either through trace of electrolyte, trace of the voltage window, but also being careful about the surface of the material to clearly see this, observe this species. So I think a good way to answer your question, also, and something we are trying to learn and do right now is, we discuss right now, is how can we also code the surface of the materials. Therefore, we avoid surface reactions that could ultimately affect the property of the bulk material we are observing. So I think with our understanding and with surface coating and with electrolyte design, I think what you answered could be possible, and we can achieve that without having, you know, the issues.
Great, thanks, Tim.
Feel free to also post your question in the chat, or you can also ask directly.
Really fantastic talk, Tim. I'm always excited to hear you give this talk. I think it's really exciting science. I'm kind of curious, and this is maybe more speculative than scientific, but do you have thoughts on where you'd expect kind of this technology to first be implemented in batteries? Like, do you think this will go right to big name electric car device stuff, or do you think there's a niche platform that might get trialed out before it gets kind of fully implemented?
That's a very good question, Harry. So, you know, like I shown on the last part of my talk, you know, it's been the O- discovery is mainly focused on the sodium systems. And from that understanding, we picked up, you know, the design principle, which is, you know, this ordered drift can actually fundamentally allow us to have the O- species. So the goal is actually to transfer this understanding to the lithium systems as well. So to answer your question in two ways, one can think of using the sodium-based systems for, you know, mainly they have been using for grid storage with the sodium systems because of their lower energy density compared to the lithium systems. So one can, you know, use this for sodium systems as they are. But if you also want to, like, you know, improve the lithium ion technology, we need to apply these principles into the lithium system. And, you know, some of our new group members are actually, you know, trying to, you know, investigate this further and transfer the understanding of the sodium system to the lithium system. So if you actually apply this to the lithium system also, then that can also be used for portable devices as well. But as it is right now for the sodium technology, it can be used for grid storage the way it is right now. But again, I think
really interesting. Thank you very much.
And again, the main thing right now is, like, you know, I discussed mainly about the oxygen redox in this system, but you can also actually access the manganese redox system in the system. I was carefully just looking at the oxygen system because I want to understand that. But if you combine the manganese and oxygen system together in this material, this is still, low hysteresis, very reversible, and it's still over very high capacity that can also be used currently in real technologies, maybe with modification on the surface and also improving the electrolyte in the materials, in the devices. Yeah.
Thank you.
Thank you, Harry. Any more questions? Feel free also to drop your questions on the chat box. Questions or comments, remarks? There is one, I think. Let's see. Okay, so Andre, thank you, Andre, for your question. He asked it about the redox kinetics of this system. So we didn't test that kind of question, but because, so the question he asked, Andre asked it is, if you do this O- or localized whole redox processes, how fast can happen compared to, like, for example, the peroxide systems or other ionic redox mechanisms? Fundamentally, the way I think of it is that, since we are involving only one electron, because going from O2-, the oxide, to O- is only one electron process, I think that fundamentally will improve the rate. But also, we have yet to do the experiment and verify this. That's why also I think it's very relevant for catalysis application, because if you want to have a higher, kinetics when you have catalytic activities, having this species that only involves one electron could actually be faster without having any intermediate steps that would slow down this mechanism, or this redox mechanism. So in short, I would hypothesize and assume that is going to be very short, but we have to test it. Is this what I can say now? But fundamentally, it should be faster.
All right. If there are no further questions, then I think this concludes the public portion of the thesis defense. Thank you, everyone, for attending, and have a great week. Tim, are we on this Zoom for the private session?
Actually,
or
I think,
different Zoom?
I think we're going to do acknowledgement first, right? Yeah.
Oh, sorry. I apologize.
No worries, no worries.
Sorry about that. Yeah,
No,
please go ahead, Tim.
Everyone stay here. No, don't go yet. I think.
Oh, we already lost a few people. I'm so sorry about that.
No worries, no worries, no worries, no worries. That's what Ricardo saw. Let's see, another message. Okay. Yeah, so anyone, if you can stay for maybe another 10 minutes. Give me a second. All right, so I guess maybe, I would like to start by talking about, my next step. Probably most of you know, and, everything that I was able to do in my PhD was possible by so many people. I will mention their names shortly, but also like the work that I have done, the mentorship that I have got so far enabled me to actually have this exciting future and exciting next steps that I'm gonna. Like most of you know, I'm heading to Berkeley as a Miller and as a presidential fellow to do my postdoc. And after that, I'm heading to MIT to be a faculty in the Department of Material Science Engineering. So I just want to say that, I think I have been able to present, and my exciting future was possible by so many people. And as one of the old African proverbs goes, it takes a village to raise a child. And I would like to also believe that it also takes a village to raise a scientist. And there's so many people who made this to be true. First, I will start by thanking the Defense Committee, everyone who made a time to actually come here today, and looking forward to the discussion after my talk. I will talk more about Tom in the next few slides, but Tom, I think we met in IBM a few years ago, and since then, you've been this positive energy person, a friend, mentor for the past few years, and I really enjoy the interaction, the chance I get to interact with you, and I'm looking forward to also communicating, collaborating, and talking to you in the future as well. Yi, it's an inspiration for a battery researcher. Things we have been able to accomplish. It's very, very remarkable. And also, as a previous Miller Fellow, I'm very happy to know that we're going to be in the same family together as the Miller Fellows. And I'm looking forward to also to continue to learn from you, to collaborate with you in the future. And Jin, we met maybe about 6-7 months ago, and I really struck me as someone who really cares about people, who really cares about the well-being and also like the holistic growth of someone. And I would like to nurture and continue our friendship and collaboration in the future as well. So with that being said, I also want to thank funding sources and facilities that have been part of to be able to do this work, and mainly the DOE, the DARE Fellowship, the Age Fellowship, and the Stanford Journal have been made it possible for me to continue my PhD research without worrying about kind of funders. And the Berkeley Light Source, ALS, and the SLAC National Laboratory have been the one that have been providing the light sources where I was able to do the X-ray measurement, the RICS, the diffraction, other methods, which are very uniquely available at our radius. And I've been very, very privileged to be doing my PhD at a place close to these amazing facilities, which are unique in the world. And also NERSC, where most of all of my calculations that I've shown today have been computed on. And then different stuff, both at Stanford SLAC, Mara, Chris, Annie, and Margot also has been bearing with me with all the nagging and questions regarding logistics, and all of this was possible through the support of this holistic agencies and people. In terms of my advisors, I tell myself I've been very, very, very fortunate actually to be able to work with Will and Tom. I think I met Will also, I think, at IBM when he came to give a talk, as I was an IBMer. But Will, struck me as someone who's very energetic, very sharp, very motivated, but also who see the talent in people and work so hard to dig that out of, to nurture and to dig that talent. And I think every time that I get a chance to work with you, talk to you, you really push the limit, push the boundary, and help me to see what can be possible and to go for it. And you mentioned about the strategy, capability that I have, but you also struck me as someone who really made good roadmaps for my pitching for the future. And I would like to continue our, friendship and relationship moving in the coming years. And this past year has been also very special, where you and I spent like several hours over the phone, almost 1 or twice a week, to help me in my application, to help me with everything that I was going through. So I really thankful for your kindness, for your time, for your sincere care for my growth, and for always being available to whenever I needed you. So thank you so much. And the future is just more exciting. It's just the beginning. Tom, I think I met you my second week, third week. And since then, you struck me as a person who's an amazing scientist, but also an amazing human being. And I think my goal in life is to strike the two balances. And the way you care for us, the way you care for me, the way you care for the whole group, and putting our life after, before the work we do. I think that's something really, while we still achieve and produce, still do good science, but we also, make us the priority, our well-being and our safety and health. And whenever we go for retreat, you were cooking for us, like for lunch and breakfast. I was like, what's going on? So it's really like we go beyond what I could envision for an advisor. You're just a father, older brother, or whatever you like to call it. And I'm really, thankful for the friendship we have and the mentorship you have been giving me and everything you taught me and in the physics arena. And I'm looking forward to also keeping our relationship and continuing our collaboration and exciting future together. In terms of collaborators, so I actually started my first year of my PhD with Tom and with Mike Tony before I also started working with you. Mike Tony is a person who was a pioneer in the X-ray / battery field, and played a crucial role in the formative years of my PhD. And even after I started working closely with Will Chu, much more, he was a key person in terms of giving me a very remarkable, very valuable advice both on my work, but also in my career as well. And he's now at Colorado Boulder as a professor, but at SLAC as a scientist. Wanli is a staff scientist at Berkeley, And all the risk measurement we were able to do were through collaboration with Wanli. Wanli is just an amazing scientist, but also an amazing person as a person. So he's always like low-key, down-to-earth person who's always very charming to talk with and work with. And Linda, I have been privileged to work with her the past 2 years, and mainly nurtured, started with the collaboration and communication they have with Wilchu. But Linda has been playing a huge role in improving my material chemistry knowledge and giving me feedback and also helped me in my rebuttals, even knowing how to write a rebuttal. I learned mainly from 3 of them, Wilchu, Tom, and Linda, but also Linda played a huge role in terms of the scientific writing in the rebuttal process. So that and making a time over the weekends to give me comment on my slides for presentation or for job talks, I really appreciate you going out of your way to be able to help me beyond just the collaboration. So I also look forward to working with you in the future. And this work that I've shown today is possible because of the brain power of these 5 people that I'm showing over here, plus their smart and brilliant staff scientists, postdoc and PhD students that have been privileged to work with. I think when you have nice people, but also very smart people, that's just the best of the best combination for a scientist. And I was very lucky to be able to, work with those people from Tom's group, Das, Brian, Chinching, and also like Sean, have been playing a great role in my PhD. And from experiment, Will Gent, Kipple, Peter C, and Grace, people at ALS and also Slack, Chintan and Jinping, and also like Linda and others, PhD students, Young Kim, they are everyone contributor to a different amount to my work, besides being a friend and also support system, but they're also really helping my growth in the past few years. I would like to give a personal shout out to like Das. Das is an amazing person and I learned a lot from him. It's always nice to learn and just build on his knowledge and wisdom. So that's an amazing person to work with. Similarly, was also Will Gent, and who actually, like Wilchu was said, the previous thesis was Will Gent thesis, and I was able to continue working on this work because of the amazing work he did before me. And then also Young, also he played a lot of role in the sodium manganese work that I have presented today. So yeah, it's possible because of these people. It takes a village to actually produce a PhD thesis. And then this group of people, an amazing group of people from both the Chu group and the Devereaux group, they be my family and also my friends in this journey. And they made it in the 5 years to go by so fast, even though there were some challenges along the way. And I thank everyone. I cannot mention people by one, but thank everyone for always being there, for providing all the support, the guidance and the mentorship throughout the years. And I've been also so privileged to have so many mentors in my life. And started with, after I came to the US 10 years ago to do my undergrad, I started my first summer working in Professor in the Hyles lab, who's Will Chu's advisor. And that was the first time I was actually doing research in my life. I did some lab experiment back home, but this was the real research. And that's opened up the whole door for me in terms of material science, in terms of energy technologies, in terms of research. And hadn't it been for the mentorship and the guidance and encouragement from Susanna from that day on, I think I wouldn't make it today. And I really have a big place for what our mentorship, our friendship, and also like things we have been able to do together so far. And then Ananda Shastri, he is my advisor in undergrad. Also, similarly, he impacted my formative years of doing research. And these are like, they lay down the basics, the foundation for the house that has been building in terms of my research growth. And then I went to IBM and I met another exceptionally amazing people. Here, Salamon Asafa, he is like almost now my older brother, almost like my mentor. He's the person I go to for anything, whether it's work, life, relationship, whatever. He's always there. He goes beyond his way to make a room to advise me in so many ways. And Huchul and Barbara, same at IBM. For sake of time, I'm not gonna mention everyone who have contributed in my work, but people I met at Salam National Lab, Princeton, Berkeley, NSF, Stanford people, my mentors, but also now my future colleagues at Berkeley and at MIT. These people really made my past to be more enjoyable, more fruitful, more, something I look forward to also riding and continuing on this journey because of the amazing network of people I have been blessed with.